Now I'm going to do what I call collapsing the Einstein field equations into Schrödinger's equation, which is the whole point of what we're doing in being able to explain the unified field theory. There's basically a region in reality, and there's a boundary. There's two regions in the world of existence. There's a region in which we can measure and a region in which we cannot. There's a region here because we can measure, we can use different mathematical techniques. Then we can use, let's say, in this region here, it could go this way, but this way makes it easier. It's got more room to write the equations. In this area, we cannot take a measure, but we can use some very intelligent approaches to be able to find out some of the things that are going on in here. Usually in here we use things like eigenvalues, the summation of an infinite number of eigenvalues, different eigenspaces, and so forth, to the solution of the complete time-dependent Schrödinger equation. Let's say in this area is ruled by a different set of differential equations. So we'll now take the Einstein field equations combined with Maxwell's equations, the Faraday tensors, which was done by Lorentz and Minkowski, put together in 1904. We have record of a paper, and in 1915 Einstein's very famous paper on general relativity includes the same derivation. So we have, completely honest, this part is the stress energy tensor, which describes tension along the field lines, which is really the stress energy tensor. This is really T mu nu, but according to usual convention, when we discuss the Einstein field equations, this is a material, and this deals with material stresses, strains, usually from elasticity and so forth. Now, this creates curvature, if you like, for which there is an equivalent acceleration that will measure a type of curvature. We are measuring that light does not seem to travel in or behave as though it's traveling in a straight line. So we will perhaps call that curvature, and that G mu nu, which is described by that, by various shapes and forms of the geodesic, is caused by stresses and strains along the field lines, which is from a material stress energy tensor plus a field stress energy tensor, and this is the field stress energy tensor using Maxwell's equations. Now, if we say there's an equivalent acceleration, if let's say we have the path of light that is traveling in a certain way, and that's a human traveling this way as a path of light. We have, let's say, someone wishes to observe it, and they're in a box, and they're eyeballing this thing, and let's say they are accelerating with some acceleration traveling this way, then it will appear curved. And what we're looking for is an equivalent acceleration that will match the curvature of the path of the ray of light, that will match the measurements we make with the Einstein tensor. So in a very overall way, in a very general statement, I can say there's an equivalent acceleration. Now, if we're using applied mathematics, we're talking about acceleration, we're talking about the second order differential, d to the psi of dt squared, and there may be units in front of this and so forth. But this in general sets us up for a particular differential equation. That's this part. If we're looking here at the stress energy tensor, the stress energy tensor is a result, delta to the fourth chi equals 0. We solve for that. This is the elasticity and so forth, the medium. And then psi xx, psi xy being the shear, psi xy down here, psi yy is the stress tensor. Now, if we add on time above this way and z's around here, we end up with the stress energy tensor. Therefore, there exists a function. There exists a function in which the acceleration is matched by stresses and strains here from the biharmonic formula. So we'll put a delta to the fourth chi here, and we know that this is a second order differential equation from Wien, and Wien's comments on the Einstein field equation, Einstein's paper, So I'm going to leave this minus sign there. B del squared psi, and then we'll have plus C, a constant, times psi. Usually with electric fields, we've got a divergence, we've got a cross product with magnetic fields. So I'm saying there exists some function of psi that matches this particular equation that describes the Einstein field equations. Now, I can collapse this to try and get Schrodinger's equation. It's a heck of a lot easier if I take Schrodinger's equation. I'll go upstairs and match this. So Schrodinger's equation times psi. Make sure I got that right? Yes, I have that right. Now, one of the techniques we can look at with differential operators, we take out the psi. So we'll move the psi here and put a bracket. We'll move the psi to the outside and put a bracket. Put a psi there. So this can be thought of as an operator on psi. This can be thought of as a complete operator also on psi. Since we can remove the psi's, may as well do that. That operator is equivalent to this operator. So if I now want to get acceleration, this is velocity, this is not acceleration. This velocity is a result of this, so we'll consider this as a velocity, as an operator, and if I apply this operator onto itself, it would be the same thing as applying this operator onto itself, and we have psi here, we have psi here. So doing this, this operator applied onto itself will be minus h bar squared day 2 psi by day t squared equals this operator being applied onto itself is h bar to the 4th over 4m squared del to the 4th psi minus twice the sum of the things in the middle, which is h bar squared times v, multiplied by 2, so that's m del squared of psi plus v squared psi. So I have now here taken this, and in this case we can now measure things that are happening with this. This is using this to measure this. This is our Heisenberg. So I can call a Heisenberg boundary. It's the Heisenberg boundary between quantum mechanics and areas where we can actually take a measurement, and we can go through and derive it and all sorts of other things and show the Pythagorean theorem and bring up G mu nu with a horrible number of differentials and various other things that we need to do. All sorts of wonder differentials over here with this incredibly complex but extremely elegant equation. We can now transfer this part here would match this part here, so there is an equivalence between here and here. I have filled out the constants now that happen to be between these things that would take place here, and we could do this and also derive back down to here. So that's basically where we're at here. What happens is we can now solve this equation according to the Heisenberg boundary conditions. Usually what I do with the Heisenberg, so that would be our Heisenberg boundary condition. When I solve this equation, if we take a look at it, and we may as well do that, let's get rid of this as a demonstration. So here we are, and we can use this as a measure. Every time we may be looking at things in here, but we're really just measuring things in a particular way because of the Heisenberg boundary. What we see is, for example, some space in here is the Heisenberg boundary and so forth, so we've got some quantum space in there. And you've got another quantum space over here, Heisenberg boundary here. But we can see these two things that could be described by a quantum space, and let's say one bangs into the other and they both go flying off in some way, and the whole thing becomes a black box. Okay, all we know is something came in and something has come out of this particular black box. That's really all we can measure. However, if we wish to go inside there, we then need to take this item here and look at the eigenvalues, that would be portrayed and generated by this particular equation in this particular region, because all we would see is what's going in, what's going out. We can't see inside, we can't have any measurement inside because of the Heisenberg boundary. Taking a look at this. And I'm feeling a little warm. It's quite hot out here in Calgary. It's the end of the day. It's a Friday night, so I'm trying to get this forward, and hopefully it's clear enough. I've noticed I made remarkably few mistakes. So if we have a second order differential equation in time, okay, we will have two eigenvalues. Okay, so we'll have two eigenvalues. Those eigenvalues, one of them will be real, one of them will be real, one of them will be imaginary. Here we have a fourth ordered, but we have three spatial units. So we have 4 times 3, 12 eigenvalues that will completely describe this according to the Wronskian. Over here, we have a second-order differential equation, the second-order differential operator. We have 3 variables, x, y, and z. So we would have 2 times 3, giving us 6 eigenvalues that would solve the Wronskian for this. This is 0th order differential, so we wouldn't have any there. So if we add 2 eigenvalues plus 12 plus 6, we end up with 20 eigenvalues. 10 of them would be real, 10 of them would be complex. We have a 20-dimensional eigenspace that is the solution to this equation. However, if ever we actually use this and take measurements and use it with boundary conditions and so forth, half of them would be real, half of them would be imaginary. Therefore, 10 real plus 10 imaginary. That's what we would have. We can only see either real or imaginary when we go to create an actual solution to the problem, and that would give us, every time we try and measure, we would not see a 20-dimensional space, we would see a 10-dimensional space, and we are free to use either the reals or the imaginaries, and we combine them, but within the same let's say eigenvalue. If we're using time, you cannot use both. If we're solving for the eigenvalue of time, you can use either a real or a complex. You can't use both. If you're using for x over here, for example, you use the real eigenvalue in x or the complex in x, so real in x or the imaginary in x, but you cannot use 2 of them. That cuts it in half. So you're only allowed 10 at a time. You may have some being real, some being imaginary, all real, all imaginary, or all imaginary, and any combination, but you can only use 10 at a time. So it's really a 20-dimensional eigenspace. We cut that in half, and there's our 10-dimensional eigenspace. Now, I've done the solution to that. I've actually seen it. You end up with Bessel functions. You end up zeta functions, Riemannian zeta functions all over the place. Some lovely stuff. And as a result of that, we can see that this fits very nicely into string theory. And I know you were saying that the person who invented string theory had lost faith in what he was doing, and he was doubting what he had done with just string theory. It's not superstring theory, which we can go on. It's actually string theory, and the original string theory with, I've seen a little bit of his work, but not that much. I haven't seen the actual equations that he had. I'd love to see them, because what I think I can do is take this mathematical criteria and combine it with his work and be able to see string theory, which I think is a beautiful, beautiful theory.